Energy in a simple harmonic oscillator is always conserved. So, for example, with a pendulum, as the pendulum swings up to the amplitudes, you have all potential energy. It's whatever maximum there and no kinetic energy, because remember, the velocity at the amplitude is going to be 0. And as it comes back down at the equilibrium, you are going to have minimal potential energy, depending on where you call your 0 for gravitational potential. You could say 0 potential energy, and you're going to have your maximum kinetic energy. And the same thing works for any object on a spring or anything else that goes through simple harmonic motion. Now, depending upon the given information, it might just be easiest to use very traditional equations. Kinetic energy equals 1/2 mv squared to calculate the velocity. Potential energy equals mgh if you know heights that the pendulum rises up to. Or maybe with the spring, you're at some point in time maybe going to have to use Hooke's law, and remembering that negative du standing for potential energy, dx equals f. If I take the integral of my force equation, I get to my potential energy equation for a spring. Potential energy of the spring, 1/2 kx squared, where x of course stands for the displacement, so maybe it would be easier to use potential energy of the spring and kinetic energy to do these problems. But that's not always the case. Sometimes whenever the thing is vibrating, what you know more about is the period of it, or other terms that come from simple harmonic motion. If that's the case, two equations that become very helpful. Total energy in simple harmonic motion is 1/2 m omega squared x naught squared. Now that equation should make sense to you, since maximum kinetic energy just from the base equation is going to be 1/2 mv naught squared, and whatever kinetic energy is maximum, you're going to have no potential energy here. Substituting in the equation for maximum velocity here. Maximum velocity is omega x naught in simple harmonic motion. You can see, because of that square, how we quickly get to that equation for total energy, because kinetic energy maximum will be my total energy. If you need to solve for the kinetic energy at any other point, not just the total energy, or aka the kinetic energy at equilibrium, because kinetic energy at equilibrium is maximum, that's going to be the total. But if you need to solve at any other point, 1/2 m omega squared, and within parentheses, x naught squared minus x squared. So the displacement away, here's your amplitude, and here's the actual position away from equilibrium. This is not just necessarily displacement from equilibrium. This is getting measured relative to the amplitude. And then, of course, simply if you need to calculate potential energy stored in the simple harmonic oscillator, then if you calculate total and you calculate kinetic and you subtract whatever you're left with would be your potential energy. Energy in your simple harmonic oscillator is conserved. Always stays the total amount of energy, always remaining the same. In this example problem, I have a 500-gram mass. It's hung on the end of a spring, and whenever it's hung on the end of the spring, it stretches by itself down 13 centimeters. And then you take your hand and you compress it maybe back up a little bit, doing 5 joules of work to do that. What is the total energy of the simple harmonic oscillator is the first question. Now your first reaction might be to jump to the total energy equation, 1/2 m omega squared x naught squared. And I don't know x naught necessarily just yet, nor do I know omega, but I do know how to get omega, right? Omega for a spring is square root of k over x, k over m, and I know the mass that's hung from it, 0.5 kilograms, and to solve for my spring constant, I come over and I use Hooke's law whenever it was just initially stretched, right? Negative kx minus mg, that's the force of the spring, minus gravity equals ma, where a is 0, and that allows me to solve for x. But it's actually a lot simpler than that, because if we consider at equilibrium this to be my 0 potential energy mark here, and there's an exchange, right? There's gravity in here, there's spring potential energy, but if we consider 0 to be 0, whenever it's at rest right here, to have 0 energy, and then we give it 5 joules, because it was at rest, if we give it 5 joules of energy there, that means the total energy is just simply going to be 5 joules. Work energy theorem. The amount of work that you do on a system is the amount of energy the system gains. Now for number 2, I'm actually going to need to go through that. What is the maximum displacement of the spring? Solving for x naught. Well, easily done. I can come back to my total energy equation because I know the total energy that it has. The only thing I don't know in this problem is what omega is, so I actually need to go through what I was talking about, solving around for my spring constant, so then I can solve for omega. And I'm going to work this in letters just to get the practice for you. Now here, the m in the numerator up here being divided by my mass down there, the masses cancel out. If you're unsure of that, imagine putting this m over 1, and then you're dividing two fractions, so you multiply by the inverse. You'll see the m's cancel. Now, I will point out this is only in this very specific case where these two masses are exactly the same. They don't necessarily have to be. You can use a mass to actually calculate your spring constant and then hang a completely different mass on there and then stretch it to cause it to oscillate. It just so happens that we did not change the mass for whenever we initially hung it on there, what we're using to calculate spring constant, and then to cause it to oscillate. Now, in reality, this would have to be a perfect spring for that to occur. Normally, with a real spring, you actually want to get it stretched a little bit ahead of time with maybe some light mass, and then add another mass on there before you actually start going through Hooke's law. And so things would be slightly different. Alright, now I know my angular frequency here, and this negative sign might really freak you out. You're thinking this turns out to be a negative number, square root of negative is going to give me an imaginary number. Well, not actually here, because this negative number here this negative here is going to cancel out, because this is the distance that you stretch, and remember, whenever you stretch it down, you're actually going to come out with a negative. Negative times a negative equals a positive. Now, whenever I actually substitute this in over here and make it square root of g over negative x, be very careful, because this x naught and that x are two different ones. This x is referring to the displacement from Hooke's law, 13 centimeters. And remember, that would be negative 13 centimeters. Negative times a negative equals a positive. On the other hand, this x naught is referring to the maximum amplitude that we would reach, or the amplitude that we would reach in vibrations. So these are two very different x's. If that really messes you up, I'd recommend going ahead and getting a number for omega and substituting the number in instead of leaving it as variables. But in this case, I'm going to leave it as variables. Squaring my square root makes those go away. So now I've substituted in all of my numbers here. You can see here negative times my negative 13. That was negative x squared, or negative x here for how far down it came in Hooke's law. But it also, remember, it went downwards, so that's why the negative 13. And whenever I multiply those together, I come out with 18.86. By the way, I made a mistake right here. There should be a decimal there, centimeters to meters, 0.13 meters for 13 centimeters for how far down it displaced from Hooke's law. And I end up with a maximum amplitude of just over 1 meter. Number 3, what is the spring's maximum velocity? Well, we know maximum velocity is omega times the amplitude. And now that we've solved for the amplitude, and we have an equation to deal with for omega here, using all of our previous calculations, this becomes very, very simple. And I come out with a maximum velocity of about 4.4 meters per second after substituting all of that in here. Just make sure that you're careful, right? Negative x, but our displacement went down whenever we were solving through here, so a negative there, and then my maximum displacement.
This is an example problem. Of course, not all problems follow this exact format, but this problem does demonstrate how to use the given equations well.